In this video we discuss the rationale for enzyme catalysis. Right, so focusing now on enzymatic reactions. The type of reaction that we're going to be studying is just a substrate turning into products. And then this reaction would be very slow if it's not catalyzed by an enzyme. But when you have an enzyme, that reaction turns to have an appreciable rate, something that will take place in a reasonable amount of time in biological media. Now, the reason that the enzyme makes the reaction faster is because it provides an alternative reaction mechanism. So the first thing that we introduce here is what type of alternative reaction mechanism you would have. All right, so when you actually have an enzyme, usually the way that we're going to study these reactions is as follows. In the first step, you're going to have that the enzyme binds to the substrate to generate an enzyme-substrate complex. Okay? And it turns out that this reaction tends to be reversible to some extent. Okay? Now, once the substrate is bound to the enzyme, reaction takes place. Okay? And we're going to consider that this reaction is actually not reversible. Okay? In most of our work. And then the products of this reaction right here would be the product bound to the enzyme, which would then need to dissociate. And this process can also be reversible. Again, this will be your near reaction mechanism, okay, for the substrate turning into product reaction when catalyzed by an enzyme. Usually, the way that we think about this is as follows. You can draw a reaction energy diagram for these two processes. We plot here energy versus reaction coordinate. Right? And the idea is that in the absence of the enzyme, the reaction would have a very high barrier. Okay, that would be your substrate to give products. Okay, this reaction is going to have a barrier which is very high, and that means, according to transition state theory, that the rate constant should be very low, and therefore the rate for the reaction is also going to be quite low. The reaction will be very, very slow. Now, when you have this alternative mechanism, then this reaction energy profile changes. Right, now we add the enzyme, and what happens is, well, the first thing that takes place is an association of the enzyme with the substrate to generate the enzyme-substrate complex. And then this is where reaction takes place, where you turn the substrate into the product, and this is going to have a different barrier that gives you your enzyme product complex. And then this enzyme product complex can dissociate, usually through a lower barrier. Okay, so as you can see, it's fairly straightforward to see that the overall barrier for the reaction in the catalyzed mechanism is actually much lower than in the uncatalyzed mechanism, and that means the rate constant will be much higher, and also the rate will be much higher as well. Alright, so now we can actually use transition state theory to see specifically how this can change. Alright, so we know that from transition state theory that the rate constant is equal to the following. Okay, so be T over H e to the entropy of activation over R, and A to the minus enthalpy of activation over RT. Right, so most of the times, the way that we understand enzymatic catalysis is through this term, okay, this enthalpy term. When you think about the energy or enthalpy requirements for the reaction to take place, it's clear that the enthalpy of activation in the uncatalyzed reaction is much greater than the enthalpy of activation in the catalyzed reaction. Right? So when you decrease that delta H, what that means is that the rate constant goes up by quite a bit at the same temperature. But something that goes unnoticed most of the time is that the entropic requirements for the reaction occasionally or sometimes also get ameliorated by the presence of a catalyst, okay, of an enzyme. We're actually going to see how this is the case for reactions that involve two substrates. Okay, so let's actually redraw this for now. Reactions that take require two substrate. Okay, so suppose the reaction that you're looking at now is A plus B to give P plus Q. Okay. And then what we're going to do now is try to write here a mechanism for the catalyzed reaction. Okay, so you will have that if there's a catalyst, then like an enzyme, then what will happen is that both substrates will need to bind to the enzyme, and there might be an order, or maybe there's no order. It could be a random or a sequential mechanism. that forms an enzyme A sub B complex, then reaction takes place, and this might be reversible. Reaction takes place, EPQ, and then this needs to dissociate the products. Okay, there will be a simple reaction mechanism for, again now, an enzyme catalyzed reaction with two substrates, A and B. Now, when we were studying here transition state theory, okay, which I'm going to rewrite right here, we noticed that the entropic term changes according to whether this reaction is unimolecular or bimolecular. Okay? We're now focusing here on this term. Right, so for a bimolecular reaction, what we said is that usually this entropy of activation terms tends to be negative, because we know that when A and B come together to form one transition state, okay, there's a loss of entropy. You have two molecules freely moving, and then at the transition state you only have one, which clearly indicates that there's a loss of entropy. So then what happens is that this delta is actually negative for that bimolecular reaction. Okay, and typical values for delta S of activation of bimolecular reactions might be something like this. Delta S might be maybe minus about 30 joules per mole Kelvin or so. Now, this situation changes when you have that the transition state or the reaction is actually unimolecular. Okay, when you have a unimolecular reaction, there's only one molecule in reagents that goes to the transition state. There might be a slight change in entropy from reagents to products, but you only have one molecule in each. Right? So the change in entropy is actually not going to be very, very large, okay, from reagents to the transition state. Right? So that entropy of activation is going to be a number close to zero, perhaps positive occasionally. Right? So again, while you have this for a bimolecular reaction, for a unimolecular reaction, this number will be typically close to zero joules per mole Kelvin. Occasionally, it will be even be positive. That's for a unimolecular reaction. Right, so something interesting that happens here when you compare the uncatalyzed reaction to the catalyzed reaction is that clearly the uncatalyzed reaction is bimolecular. Okay, but when you have the catalyzed reaction, the rate limiting step, the step that usually has higher barrier, actually happens to be unimolecular. You have one species turning into another species, right? So when you go, the transition state will be right in the middle, right here, and the entropy of activation in this rate limiting step will be zero or even positive. Okay, so and that would not be the case when you actually have this reaction in the absence of a catalyst, right? So while the catalyst will decrease the enthalpy of activation, and that makes the reaction faster, it actually also makes this turn favorable, because you have that in enzyme catalyzed reactions, usually the rate limiting step is unimolecular, and that does not have a large entropic penalty. Okay, so if you actually calculate this term for the bimolecular reaction that is uncatalyzed, and for the catalyzed reaction in which you have a unimolecular step, right? The difference in this term between having these two values is about a factor of 37. Okay, so even if the barrier was not changed at all by the enzyme, okay, yes, the entropy requirements would make the catalyzed reaction 37 times faster than the uncatalyzed reaction. Okay, so in summary, we have learned that once we examine the reaction mechanism of an enzyme catalyzed reaction, what happens is that we can rationalize the increase in the rate of the reaction by a decrease generally in the enthalpy of activation. Okay, the enzyme provides an alternative mechanism that usually has a lower barrier. However, under some circumstances, for example in bimolecular reactions, okay, the enzyme catalyzed reaction also enhances the rate because it has lower entropic requirements for the reaction.